The story of Neptune does not begin with a gaze through a lens, but with the tip of a quill on paper. Unlike all other planets in the solar system known by the mid-19th century, Neptune was first discovered through mathematical calculations before being visually confirmed. It all began with the rebellious behavior of Uranus. Following its discovery in 1781 by William Herschel, astronomers noticed that Uranus did not follow the orbit predicted by Kepler's laws and Newton's law of universal gravitation. The law of universal gravitation, formulated by Isaac Newton in 1687, states that the force of attraction between two bodies is directly proportional to the product of their masses and inversely proportional to the square of the distance separating them. In discursive terms, the gravitational force is equal to the gravitational constant times the mass of the first object times the mass of the second object, all divided by the distance between them squared. This law is the pillar that keeps planets in orbit and allowed for the prediction that something invisible was tugging Uranus out of its expected course. Two mathematicians, working independently, reached the same conclusion. An eighth planet must exist beyond Uranus to account for these perturbations. John Couch Adams, a young British mathematician, calculated the probable position of the new planet in 1843. His importance lies in the pioneering application of orbital perturbations, though bureaucracy at the Greenwich Observatory delayed the visual search based on his data. Almost simultaneously, Urbain Le Verrier, a French mathematician, used celestial mechanics calculations with impressive precision and sent his coordinates to the German astronomer Johann Gottfried Galle. Le Verrier is often remembered as the man who discovered a planet with the tip of his pen. On September 23, 1846, just 1 hour after starting the search at the Berlin Observatory, Galle found Neptune less than 1 degree away from where Le Verrier had predicted. This date marks the pinnacle of classical celestial mechanics, the definitive proof that the laws of physics governing Earth are universal and applicable to the depths of space. Neptune inhabits the outermost regions of our system, at an average distance of 2.8 billion miles from the Sun. To give an idea of the scale, sunlight, which takes about 8 minutes to reach Earth, takes approximately 4 hours and 10 minutes to reach the cloud tops of Neptune. The planet formed about 4.5 billion years ago, along with the rest of the solar system. Confirmed studies suggest that Neptune and Uranus formed much closer to the Sun and migrated outward in a process of gravitational instability known as the Nice model. This theory proposes that the gas giants migrated from their initial orbits. During this migration, the gravitational interaction between the large planets and the remnants of the solar formation pushed Neptune to its current position, clearing the path and shaping what we know today as the Kuiper Belt. Neptune is classified as an ice giant, a crucial distinction from gas giants like Jupiter and Saturn. Although 80% or more of its mass is composed of a hot, dense fluid of icy materials, water, methane, and ammonia, over a rocky core, it has an atmosphere predominantly of hydrogen and helium. Methane, a chemical compound made of 1 carbon atom and 4 hydrogen atoms, is responsible for the planet's deep blue color. In Neptune's upper atmosphere, methane absorbs red light from the visible spectrum and reflects blue light back into space. Interestingly, Neptune appears a much more vibrant blue than Uranus, despite having similar chemical compositions. Recent research suggests that a layer of organic haze is thicker on Uranus, which lightens its appearance, while Neptune's atmosphere is more efficient at removing this haze through intense meteorological processes. Neptune's mass is about 17 times that of Earth, and its volume is equivalent to 58 Earths. Its gravity at the surface, or rather, the cloud tops, since there is no solid surface, is only 14% stronger than Earth's. This is because while it is very massive, its radius is also large, which reduces the gravitational force felt at that distance from the center. The acceleration of gravity on Neptune is approximately 36 feet per second squared. This world is a place of dynamic extremes. Despite being the farthest planet from the Sun and receiving only a tiny fraction of the solar energy Earth receives, Neptune has the fastest winds in the solar system. These winds can reach speeds exceeding 1,300 miles per hour, defying initial expectations that such a cold world would be geologically dead or atmospherically calm. The energy driving these colossal storms does not come from the Sun, but from a mysterious internal heat that the planet still retains since its formation. Neptune radiates 2.6 times more energy than it receives from our star. Neptune's internal heat, as mentioned previously, remains one of the greatest enigmas in modern astrophysics. While most planets radiate only what they receive or the residual heat from gravitational contraction, Neptune's energy source is so potent that it generates weather systems more violent than those of Jupiter. This process is explained by thermodynamics, specifically through the conservation of energy and the heat flow from a warmer body to a cooler one. The total internal energy of a system is the sum of the kinetic and potential energies of its molecules. In Neptune's case, this remaining thermal energy leaks into space, creating massive convection currents that fuel supersonic winds. These winds sustain impressive atmospheric structures, such as the Great Dark Spot, first observed in 1989. The Voyager 2 spacecraft, launched by NASA on August 20, 1977, remains the only human mission to visit the Neptunian system. Its importance is incalculable, as it transformed Neptune from a blurry blue in telescopes into a geographically complex world. Voyager 2 utilized a technique called gravity assist, which relies on the conservation of linear momentum and the transfer of orbital energy from a planet to a probe. Linear momentum is defined as the product of an object's mass and its velocity. In an isolated system, the total momentum remains constant. During a gravity assist, the spacecraft steals an infinitesimal fraction of the planet's orbital energy to accelerate its own velocity relative to the Sun, allowing it to reach the depths of the solar system without carrying impossible amounts of fuel. Neptune's atmosphere is composed of about 80% hydrogen, 19% helium, and traces of methane. Helium, the second most abundant element in the universe, has an extremely stable atomic structure with 2 protons and 2 neutrons. On Neptune, helium and hydrogen are not just gases. Deep within the planet, under pressures that exceed millions of times the atmospheric pressure at sea level on Earth, they behave as supercritical fluids. A supercritical fluid occurs when the temperature and pressure of a substance exceed its critical point, where liquid and gas phases become indistinguishable. In these crushing depths, scientific theories and computer simulations suggest the occurrence of diamond rain. Methane, under extreme pressure, has its hydrocarbon molecules broken apart. The carbon then crystallizes into diamond form and sinks toward Neptune's core. Pressure in a fluid is calculated by multiplying the fluid's density by the acceleration of gravity and the depth. In discursive terms, pressure is equal to density times gravity times the height of the fluid column above the point. On Neptune, because both density and gravity are high, the pressure increases drastically for every mile toward the center, reaching values where carbon is forced to rearrange into ultradense molecular structures, such as diamond. Beyond the atmosphere, Neptune possesses a system of faint, fragmented rings. Unlike the rings of Saturn, which are bright and composed mostly of pure water ice, Neptune's rings are dark and contain a large amount of organic compounds processed by radiation, called tholins. These rings were confirmed by Voyager 2 in 1989, but had been predicted by stellar occultation observations in the 1980s by astronomers such as André Breuic and William Hubbard. Breuic's importance lies in the discovery of Neptune's arcs, regions where the ring material is denser due to gravitational resonances with nearby moons. Neptune's moons are a chapter of their own, totaling 16 known satellites to date. The largest of them, Triton, is one of the most exotic objects in the solar system. Discovered by William Lassell on October 10, 1846, just 17 days after the discovery of the planet itself, Triton is the only large moon in the solar system that possesses a retrograde orbit. This means it orbits Neptune in the opposite direction of the planet's rotation. This orbital characteristic suggests that Triton did not form alongside Neptune but was a Kuiper belt object captured by the giant's gravity. The Kuiper belt is a region beyond Neptune filled with icy bodies and remnants from the solar system's formation. Triton's capture would have generated immense gravitational chaos, destroying Neptune's original moon system and heating Triton's interior through tidal forces. Tidal forces occur due to the gravitational gradient. In simple terms, Neptune's gravity pulls the side of Triton that is closer with more force than the side that is farther away. Since Triton is in an eccentric and retrograde orbit, this difference in force causes physical flexing within the moon's body, generating heat through internal friction. This heat is what allows Triton to be geologically active, featuring cryovolcanism, where volcanoes spit liquid nitrogen and dust instead of lava. Triton's cryovolcanism, as mentioned previously, redefines our understanding of geological activity on icy worlds. Instead of molten rock, these volcanoes expel liquid nitrogen, methane, and dust compounds that rise as high as 5 miles into the Moon's thin atmosphere. Nitrogen, which makes up about 78% of the air we breathe on Earth, exists in liquid and solid states on Triton due to extreme temperatures, reaching 391 degrees Fahrenheit below zero. At this temperature, molecular motion is so reduced that it nearly approaches the physical limit of absolute cold. Triton's atmosphere, though extremely thin, has a complex structure. It is composed primarily of nitrogen with traces of methane and carbon monoxide. The atmospheric pressure on Triton's surface is only 14 microbars, which is equivalent to about 1/70th, 0.000th of the sea level pressure on Earth. However, this pressure is enough to sustain winds and a seasonal sublimation cycle. Sublimation is the phase transition where a substance passes directly from the solid state to the gaseous state without passing through the liquid state. This occurs when the vapor pressure of the substance is higher than the local atmospheric pressure and the temperature is slightly raised. In Triton's case, the minimal sunlight is sufficient to sublimate nitrogen ice, creating a seasonal atmosphere that moves from one pole to the other as the Moon's tilt relative to the Sun changes. The relationship between Neptune and Triton is, however, a tragedy foretold by celestial mechanics. Due to its retrograde orbit and the tidal forces mentioned previously, Triton is losing orbital energy. This means the Moon is slowly spiraling toward the planet. Mathematical calculations based on the conservation of angular momentum and energy dissipation indicate that in about 3.6 billion years, Triton will cross the so-called Roche limit. The Roche limit, theorized by French astronomer Édouard Roche in 1848, is the minimum distance from a planet at which an object held together only by its own gravity will begin to disintegrate due to the planet's tidal forces. In discursive terms, the Roche limit is equal to the planet's radius times the cube root of 2 times the planet's density divided by the satellite's density. When Triton crosses this limit, Neptune's tidal forces will be stronger than the gravity holding the Moon together. Triton will be torn apart, and its remains will form a spectacular and bright ring system, potentially surpassing Saturn's rings in mass and beauty. In addition to Triton, Neptune's other moons, such as Proteus, Larissa, and Nereid, offer clues about the system's violent past. Proteus, the second largest moon, has an irregular shape and a heavily cratered surface, indicating it was never heated enough to become spherical through hydrostatic equilibrium. Hydrostatic equilibrium occurs when the compression force of a body's gravity is balanced by its internal pressure. In the case of celestial bodies, when an object has enough mass, its own gravity shapes it into an approximately spherical form. The importance of this concept lies in the classification of planets and dwarf planets by the International Astronomical Union. If a body does not reach hydrostatic equilibrium, it is generally classified as a small solar system body or an irregular satellite. The exploration of Neptune after Voyager 2 has been conducted exclusively by space telescopes and high-tech ground-based observatories. The Hubble Space Telescope, launched on April 24, 1990, has monitored Neptune's climate changes for decades. Thanks to Hubble, astronomers discovered that the Great Dark Spot observed by Voyager disappeared in the 1990s, only for new spots to appear at different latitudes. This proves that Neptune's atmosphere is much more dynamic and variable than previously thought. In 2022, the James Webb Space Telescope, a collaboration between NASA, ESA, and CSA, provided the sharpest images of Neptune's rings in over 30 years. Operating in the infrared spectrum, James Webb revealed unprecedented details of cloud composition and the planet's thermal structure. Infrared light has longer wavelengths than visible light, allowing it to penetrate dust layers and reveal heat emitted by celestial objects that would be invisible to our eyes. The atmospheric dynamics of Neptune, as mentioned previously, are driven by processes that defy the logic of solar distance. To understand the meteorology of this giant, we must analyze the concept of thermal convection. Convection is the heat transfer process in fluids, liquids, or gases, where warmer material, being less dense, rises, and cooler, denser material sinks. On Neptune, heat from the core warms the lower layers of the atmosphere, causing gases like methane and hydrogen to rise in massive columns, creating storms that can last for years. Unlike Earth, where meteorology is dictated by differential solar heating between the equator and the poles, Neptune's primary source is internal. This results in a phenomenon called superrotation, where the atmosphere moves at speeds that exceed the rotation of the planetary core itself. A day on Neptune lasts approximately 16 hours and 6 minutes, but its equatorial winds blow in the opposite direction of the planet's rotation, reaching marks of 1,300 miles per hour. The Coriolis effect is an apparent force that acts on objects in motion within a rotating reference frame, such as a planet. In discursive terms, the Coriolis force is equal to 2 times the mass of the object times its velocity times the angular velocity of the planet's rotation times the sine of the latitude. It is this force that curves Neptune's winds, transforming vertical convection currents into the horizontal patterns of zonal winds and large vortices we observe. These vortices manifest as the famous dark spots. The importance of monitoring these spots, as done by astronomer Lawrence Shromovsky using the Keck Observatory in Hawaii, lies in understanding how energy is dissipated in high-pressure atmospheres. Neptune's dark spots are high-pressure systems, anticyclones, that, interestingly, appear to emerge and disappear on timescales of just 2 to 6 years, a much higher volatility than observed in Jupiter's Great Red Spot. A fascinating aspect of Neptunian chemistry is the presence of methane ice crystals at high altitudes, forming cirrus-like clouds. However, while terrestrial cirrus clouds are made of water ice crystals, Neptune's are composed of condensed hydrocarbons. The condensation process occurs when a gas is cooled below its dew point, turning into liquid or solid. On Neptune, this happens at temperatures of about 330 degrees Fahrenheit below zero. Neptune's magnetosphere also presents extraordinary irregularities. Discovered by Voyager 2 in 1989, the planet's magnetic structure is tilted 47 degrees relative to its rotational axis and is offset from the planet's physical center by about 8,400 miles. This means the magnetic field is not generated by a solid iron core, like on Earth, but rather by a dynamo in a fluid, electrically conductive layer, possibly an ocean of ionized water and ammonia. Dynamo theory explains how a celestial body generates a magnetic field through the movement of internal conductive fluids. For a dynamo to work, 3 components are needed: an electrically conductive fluid, energy to move that fluid, convection, and the planet's rotation to organize the movement. In Neptune's case, ionic water, where water molecules are broken into hydrogen and oxygen ions under extreme pressure, acts as this conductive fluid, creating a chaotic and asymmetric magnetic field. The importance of this magnetosphere lies in protecting the planet from the solar wind. The solar wind is a constant stream of charged particles, mainly protons and electrons, emitted by the Sun at speeds of about 1 million miles per hour. Without a strong magnetosphere, Neptune's atmosphere would be gradually eroded by solar radiation over billions of years. The interaction between the solar wind and Neptune's magnetic field also creates auroras, though these are much weaker and more complex than Earth's due to the bizarre geometry of the magnetic field. Beyond natural phenomena, the history of Neptune's discoveries involved the use of spectroscopy, an essential technique in modern astronomy. Spectroscopy consists of decomposing the light from an object into its component colors, the spectrum, to identify chemical signatures. Each element or molecule absorbs and emits light at specific wavelengths, functioning like a fingerprint. It was through spectroscopy that astronomers like Gerard Kuiper confirmed the presence of methane in Neptune's atmosphere in 1944. The exploration of Neptune's depths leads us to consider the internal structure of the planet, which, as mentioned previously, radically differs from that of gas giants. While Jupiter and Saturn are composed almost entirely of hydrogen and helium, Neptune possesses a mantle that makes up the bulk of its mass. This mantle is not made of ice in the conventional sense, like the water ice we find in a freezer, but rather a hot, dense supercritical fluid. This state of matter occurs due to a physics concept known as the equation of state. In discursive terms, pressure is equal to the density times a gas-specific constant times the temperature. Deep within Neptune, the pressure reaches values of approximately 1.45 million pounds per square inch, which is about 100,000 times the atmospheric pressure of Earth. Under these conditions, water, ammonia, and methane molecules are squeezed such that chemical bonds begin to behave in exotic ways, creating what scientists call superionic water. Proposed by theorists such as Pierfranco de Montes in 1988, superionic water is a state where oxygen atoms crystallize into a solid lattice, while hydrogen nuclei, protons, flow freely through that lattice like a liquid. This makes the material an excellent conductor of electricity, which is fundamental to explaining Neptune's misaligned magnetic field. The importance of this discovery, confirmed in a laboratory only in 2018 through high-power laser experiments, validates mathematical models that predicted the behavior of matter under planetary pressures. Below this fluid mantle lies Neptune's core. It is estimated that the core is composed of rock, silicates, and metals such as iron and nickel, possessing a mass about 1.2 times greater than that of Earth. The temperature at the center of the planet can reach 9,200 degrees Fahrenheit, a temperature comparable to the surface of the Sun. However, the core remains solid or extremely dense due to the crushing pressure, which prevents atoms from moving apart, a practical example of the third law of thermodynamics applied to high-pressure systems. Thermodynamics also helps us understand the planet's energy balance. Neptune has a low bond albedo. Albedo is a dimensionless measure that indicates the proportion of solar radiation reflected by a celestial body back into space. In discursive terms, albedo is equal to the reflected energy divided by the incident energy. Neptune has an albedo of approximately 0.29, meaning it absorbs about 71% of the sunlight that hits it. Even so, this absorption is minimal compared to the heat coming from within, sustaining the colossal storms mentioned previously. One of these storms, which followed the original Great Dark Spot of 1989, was the Northern Great Dark Spot, observed by the Hubble telescope in 1994. The importance of these continuous observations lies in the verification that Neptune has seasons, although each season lasts about 40 Earth years. Since Neptune takes 164 years and 9 months to complete one orbit around the Sun, it has only completed one full orbit since it was discovered in 1846. This milestone occurred in 2011. During this long Neptunian year, the planet's axial tilt of 28 degrees, very similar to Earth's, which is 23.5 degrees, causes different hemispheres to receive varying amounts of solar radiation over decades. This causes slow but massive changes in cloud opacity and the intensity of atmospheric bands. Scientists such as Heidi Hammel, one of the leading experts on giant planets, have used this data to formulate global circulation models. Hammel's importance in the field of planetary astronomy is highlighted by her leadership in the Voyager 2 team and her strategic use of Hubble to prove that ice giants are not static worlds. Her research confirmed that Neptune's stratosphere is warmer than that of Uranus, possibly due to the presence of hydrocarbons that absorb heat more efficiently. The chemistry of Neptune's stratosphere is influenced by photolysis. Photolysis is a chemical process in which photons of sunlight break down molecules. In Neptune's case, ultraviolet radiation breaks methane, 1 carbon and 4 hydrogens, into free radicals, which then recombine to form heavier molecules such as ethane, 2 carbons and 6 hydrogens, and acetylene, 2 carbons and 2 hydrogens. These molecules descend to deeper layers where they condense, forming the hazes that give depth to the planet's visual appearance. The interactions between Neptune and the surrounding space environment are mediated by the Kuiper Belt, a vast region of icy debris extending beyond its orbit. Neptune plays the role of a gravitational shepherd over these objects, a phenomenon explained by orbital resonance. Resonance occurs when two orbiting bodies exert periodic gravitational influence on each other, typically because their orbital periods are related by a ratio of small integers. Resonance can be described by the relationship where the number of orbits of object A times its period equals the number of orbits of object B times its period. In discursive terms, the orbital frequency of the first body multiplied by an integer is equal to the orbital frequency of the second body multiplied by another integer. The most famous example is Pluto, which is in a 2-to-3 resonance with Neptune. For every 3 laps Neptune completes around the Sun, Pluto completes exactly 2. This mathematical harmony prevents the two bodies from colliding, even though their orbits cross. The importance of this dynamic was consolidated by astronomers such as Jane Liu and David Jewett, who in 1992 discovered the first Kuiper belt object after Pluto. Their work proved that Neptune is not alone in the void, but rather at the edge of a third zone of the solar system. Neptune's influence is so massive that it created a gravitational gap known as the Kuiper cliff, where the density of objects drops drastically beyond a certain distance, likely due to the planetary migration mentioned previously. Looking at the physical properties of Neptune's small inner satellites, such as Naiad and Thalassa, we find a fascinating example of an orbital dance. In 2019, researchers from the SETI Institute discovered that these two moons are locked in an orbital variation resonance never seen before. Naiad travels in a zigzag orbit relative to Thalassa, a maneuver necessary to maintain stability in a system where the giant planet's gravity is overwhelming. The stability of an orbital system is often analyzed through the n-body problem. This is a classic problem of celestial mechanics that attempts to predict the positions and velocities of a group of celestial objects interacting gravitationally with each other. In discursive terms, the acceleration of each body is the result of the sum of all gravitational forces exerted by all other bodies in the system, divided by its own mass. Since there is no general mathematical solution for more than two bodies, except in specific cases, astronomers use high-precision computer simulations to predict the future of Neptune's moons. Regarding future exploration, the international scientific community, led by groups such as NASA's Outer Planets Assessment Group, has been developing concepts for a dedicated mission called Neptune Odyssey. The importance of a long-term mission, which would include an orbiter and an atmospheric probe, would be to answer why Neptune emits so much internal heat and how its magnetosphere behaves so erratically. The trip to Neptune, given the distance of 2.8 billion miles, would require the use of radioisotope thermoelectric generators. A radioisotope generator converts the heat released by the natural decay of radioactive elements, such as plutonium-238, into electricity through the Seebeck effect. The Seebeck effect occurs when a temperature difference between two different electrical conductors or semiconductors produces a potential difference, voltage, between the two substances. Since sunlight at Neptune is 900 times weaker than on Earth, conventional solar panels would be ineffective for powering a complex probe in that region. In addition to propulsion and energy technology, the future of Neptune involves studies on the habitable zone and astrobiology. While Neptune itself is hostile to life as we know it, Triton is considered one of the most promising ocean worlds. Studies suggest that beneath Triton's crust of ice, a liquid water ocean may exist, maintained by tidal heating. The existence of a liquid solvent, an energy source, and organic chemical elements are the three pillars necessary for life. The possibility of internal oceans on moons like Triton, as mentioned previously, opens a fascinating debate about the chemical evolution of distant planetary systems. If Triton possesses an ocean beneath its crust of nitrogen and water ice, the chemistry of that environment would be heavily influenced by ammonia. Ammonia acts as an antifreeze, lowering the freezing point of water. The freezing point is the temperature at which a substance changes from a liquid to a solid state. In discursive terms, the change in the freezing temperature is equal to the cryoscopic constant of the solvent multiplied by the molality of the solute. This means that by adding substances such as salts or ammonia to water, the temperature required for it to freeze decreases significantly, allowing for the existence of liquid water on worlds where the external temperature is near absolute zero. The importance of understanding these chemical processes on Neptune and its moons extends to the search for exoplanets. Currently, the most common category of planets discovered by missions such as Kepler and TESS, Transiting Exoplanet Survey Satellite, are the so-called mini-Neptunes. These are planets with radii between that of Earth and Neptune. The importance of these discoveries lies in the fact that Neptune serves as the standard laboratory for us to understand a vast population of planets throughout our galaxy. When analyzing the light from distant stars passing through the atmosphere of a mini-Neptune, astronomers utilize transit spectroscopy. This technique allows for measuring the decrease in the star's brightness at different wavelengths. In discursive terms, the transit depth is equal to the square of the planet's radius divided by the square of the star's radius. If the planet has a methane atmosphere like Neptune, it will block specific wavelengths, revealing its chemical composition from light years away. The physics of high-pressure atmospheres on Neptune also leads us to the study of atmospheric waves. In 2021, confirmed studies through infrared observations detected gravity waves, not to be confused with gravitational waves from relativity, in the Neptunian stratosphere. Gravity waves are oscillations generated in an atmospheric fluid when a parcel of air is displaced vertically and gravity acts as the restoring force to bring it back to equilibrium. In discursive terms, the frequency of oscillation, known as the Brunt-Väisälä frequency, is equal to the square root of gravity divided by the potential temperature multiplied by the variation of potential temperature with respect to height. These waves are crucial for transporting energy from the lower layers to the upper layers of the atmosphere, explaining why Neptune's upper region is warmer than expected. The history of Neptune's cartography is also filled with technical breakthroughs. Before Voyager 2, the best images of Neptune showed only a bluish disk with no prominent features. It required the development of adaptive optics in ground-based telescopes for us to see details from Earth. Adaptive optics is a system that deforms the secondary mirror of a telescope in real time, hundreds of times per second, to compensate for the turbulence of Earth's atmosphere. The importance of this technology, successfully implemented at the Very Large Telescope, VLT, in Chile, allowed astronomers to monitor Neptune's weather with a resolution that rivals space telescopes. In 2023, these observations revealed a surprising decline in Neptune's cloud cover, which appears to be correlated with the solar cycle. The solar cycle is a periodic variation of approximately 11 years in the Sun's activity, manifested by changes in the number of sunspots and the emission of ultraviolet radiation. Although Neptune receives little light, the variation in ultraviolet radiation appears to be sufficient to alter methane photolysis rates, affecting the formation of cloud condensation nuclei. In discursive terms, the rate of a chemical reaction is directly proportional to the flux of photons incident upon the atmospheric molecules. The study of Neptune's storms also revealed the existence of transient dark spots. Unlike the original Great Dark Spot, which seemed anchored at certain latitudes, these newer storms show erratic drift movements. The importance of understanding this drift lies in modeling deep atmospheric viscosity, a parameter that indicates a fluid's resistance to flow. The study of the longevity of storms on Neptune brings us to one of the most recent and intriguing discoveries of the last decade: the interaction between storms and planetary waves known as Rossby waves. These waves are giant oscillations in the atmosphere caused by the variation of the Coriolis effect with latitude. In discursive terms, the speed of a Rossby wave is equal to the zonal wind speed minus the variation of the Coriolis parameter divided by the square of the total wave number. The importance of these waves lies in their ability to trap high-pressure systems, like the dark spots, preventing them from dissipating quickly. However, in 2020, the Hubble telescope captured an unprecedented phenomenon: a dark spot moving toward the equator, where it should have been destroyed by the reduced Coriolis effect, suddenly reversed its course and drifted back north. This behavior suggests that the vertical structure of Neptune's atmosphere possesses wind shear layers much more complex than current models predicted. To understand what keeps these structures cohesive, scientists turn to computational fluid dynamics. A key concept here is the Rossby number, a dimensionless quantity that describes the importance of Coriolis acceleration relative to advective acceleration. In discursive terms, the Rossby number is equal to the fluid velocity divided by the product of the Coriolis parameter and the characteristic length scale of the system. When this number is small, as on Neptune, the planet's rotation dominates fluid movement, allowing for the formation of stable, long-lasting vortices. While the atmosphere exhibits this visual violence, the planet's gravity fields reveal secrets about its interior. Through Doppler tracking of radio signals from Voyager 2 and precise measurements of orbital perturbations of its moons, astronomers mapped Neptune's gravitational coefficients. The gravitational potential of a planet that is not perfectly spherical is described by an expansion in Legendre polynomials. In discursive terms, the potential is equal to the gravitational constant times the mass divided by the distance, multiplied by a series of terms that account for polar flattening and internal mass distribution. The importance of these calculations, led by researchers such as Caspi and Galanti, revealed that Neptune's winds penetrate to about 680 miles deep, involving a mass equivalent to hundreds of Earths in perpetual motion. Deep chemical composition also raises questions about magnetism. As mentioned previously, superionic water is the primary candidate for the dynamo, but studies published in 2024 suggest that ammonia may play an even larger role. Ammonia, composed of one nitrogen atom and 3 hydrogen atoms, can transform into a metallic state under Neptune's pressures. This theory describes how certain substances that normally do not conduct electricity, insulators, can become conductive, metals, when subjected to pressures so high that their electron orbits begin to overlap. In discursive terms, conductivity increases drastically when pressure forces electrons to become delocalized from their original atoms. If ammonia becomes metallic in Neptune's mantle, it would contribute to the generation of a complex, multipolar magnetic field, explaining why Neptune does not have a simple magnetic dipole like Earth's. Neptune's influence also extends to planetary defense and the understanding of solar system evolution. Neptune acts as a barrier and, occasionally, as a slingshot for long-period comets coming from the Oort cloud. The Oort cloud is a theoretical sphere of trillions of icy objects surrounding the solar system at distances up to 2 light-years. When a comet is gravitationally disturbed by a nearby star, it plunges toward the Sun. As it passes near Neptune, the planet's enormous gravity can alter the comet's trajectory, sending it out of the solar system or into a short-period orbit that crosses Earth's path. The historical importance of Neptune in this gravitational rail clearing is what allowed the inner solar system to become a relatively stable place for the development of life. The influence of Neptune over the outer solar system leads us to the analysis of its relationship with the so-called Centaurs and Neptune family comets. Centaurs are a class of celestial bodies that orbit between Jupiter and Neptune, possessing characteristics of both asteroids and comets. Due to the gravitational influence of the ice giants, the orbits of Centaurs are unstable, with an orbital life expectancy of only a few million years. The dynamics of these objects are governed by deterministic chaos. In physics and mathematics, chaos does not mean a lack of order, but rather an extreme sensitivity to initial conditions. In discursive terms, small deviations in the initial position or velocity of an object result in completely different future trajectories after a few gravitational interactions. Neptune's importance here is that of a scattering engine. It captures objects from the Kuiper belt and launches them into the inner solar system, where they can become active comets. When we observe Neptune's thermal properties, we find a curious phenomenon at its polar coordinates. In 2007, through an infrared observatory in Chile, astronomers discovered that Neptune's south pole is about 18 degrees Fahrenheit warmer than the rest of the planet. This hot spot allows methane gas, which would normally be frozen in the upper layers, to escape into the stratosphere. The temperature of a planet or star can be estimated using the Stefan-Boltzmann law. In discursive terms, the total energy radiated per unit area of a blackbody is directly proportional to the 4th power of its absolute temperature. This means that small variations in the temperature measured by our instruments represent significant changes in the internal energy that Neptune is releasing through its pole. The importance of this thermal vent is that it creates a unique chemical cycle, where hydrocarbons are transported vertically much more efficiently than on Uranus. This reinforces the theory that the clarity of Neptune's atmosphere, compared to its neighbor, is maintained by this leakage of heat and gases that clears the upper organic hazes. Looking toward the future of astronomical observation, the 2030s and 2040s promise to be the golden age for ice giants. With the commencement of operations for 30-meter class telescopes, such as the Extremely Large Telescope, ELT, we will be able to resolve details of Neptune's atmosphere that were previously only possible with space probes. The angular resolution of a telescope, which determines its ability to see small details, is calculated by dividing the wavelength of light by the diameter of the mirror. In discursive terms, the larger the diameter of the mirror, the smaller the detail the telescope can distinguish in the sky. The importance of the ELT for Neptunian science will be the ability to map the composition of the rings and small moons in real time. Neptune's rings, Gal, Le Verrier, Lassell, Arago, and Adams, are dynamic structures that undergo constant changes due to micrometeoroid bombardment and interactions with the magnetospheric plasma. Plasma is the fourth state of matter, consisting of an ionized gas where electrons have been stripped from their atoms. Neptune's magnetosphere is filled with this plasma, primarily originating from particles escaping Triton's atmosphere. When these charged particles strike the dust grains of the rings, they cause sputtering, or atomic erosion, turning ice into gas and causing the rings to slowly vanish over millions of years. Furthermore, NASA and the ESA, European Space Agency, are discussing the possibility of a joint mission to launch an atmospheric probe that would dive into Neptune. The technical challenge is immense. The probe would need a heat shield capable of withstanding entry speeds of tens of thousands of miles per hour and pressures of hundreds of atmospheres. The importance of such a mission would be to directly measure the abundance of noble gases, such as neon and argon, which serve as chemical fossils of the original solar nebula from which all planets were born. As we reach the final horizon of our journey through Neptune, we look toward the future predictions that science holds for this world. In the long term, the evolution of the solar system is dictated by the life cycle of the Sun. In about 5 billion years, our star will exhaust its hydrogen fuel and enter the red giant phase. Nuclear fusion is the process where light atomic nuclei combine to form heavier nuclei, releasing energy according to the equation where energy is equal to the mass lost times the speed of light squared. In the Sun, hydrogen fuses into helium. When the hydrogen runs out, the core contracts and heats up until helium begins to fuse into carbon, causing the Sun's outer layers to expand drastically. The importance of this event for Neptune is paradoxical. While Earth will likely be consumed or rendered uninhabitable by solar expansion, the habitable zone, the region where temperatures allow for the existence of liquid water, will shift to the outer solar system. For a few million years, Neptune and its moons will receive an amount of solar energy comparable to what Earth receives today. Triton, with its vast stores of ice, could transform into a global ocean world, offering a brief refuge for prebiotic chemistry in a dying solar system. However, before the Sun becomes a red giant, Neptune will continue its silent gravitational dance. Long-term orbital stability studies, using Lagrange's equations, suggest that the solar system is marginally stable. Lagrange's equations reformulate classical mechanics using energy instead of forces. In discursive terms, the time derivative of the partial derivative of kinetic energy with respect to velocity is equal to the partial derivative of kinetic energy minus potential energy with respect to position. These equations allow us to predict that, on scales of billions of years, small interactions between Neptune and the other giant planets may cause variations in orbital eccentricities, but Neptune will remain the outer guardian of the solar system. The cultural and scientific importance of Neptune lies in its status as the boundary of the classical. Beyond it, we enter the realm of trans-Neptunian objects and interstellar space. Neptune is the final reminder that the universe operates under precise mathematical laws, yet it still holds mysteries that sunlight can barely illuminate. From the precision of Le Verrier's calculations in 1846 to the infrared images from James Webb in 2022, our understanding of Neptune has evolved from a wandering point of light into a complex laboratory of high-pressure physics, hydrocarbon chemistry, and fluid dynamics. The future holds missions that will touch its clouds and possibly navigate the internal oceans of its moons, confirming or refuting the theories we have discussed. Neptune is not just a planet. It is proof that human curiosity, armed with mathematics and physics, can reach and understand worlds that are billions of miles away. It remains there, an azure giant shrouded in supersonic winds and diamond rains, waiting for the next time humanity decides to cross the spatial abyss to decipher its secrets.